All right, so with chapter 10, we're going to be looking at air pollution. And when we're thinking about air pollution, it comes from a whole bunch of different sources. And there's also going to be a whole bunch of different types of air pollutants. You can see just a couple of quick ones here. We're going to go through a whole bunch of them as we go through this chapter. But with air pollution, it's going to be a tricky topic to deal with, just because it is going to be, like a lot of these topics we talk about, just going to have a whole bunch of different sources of these pollutants, and it's just going to be coming from a whole bunch of different places. But with air pollution, one positive to point out, just to start, is there has been very noticeable improvements within the air quality of certain locations when those locations have kind of decided to put that at the forefront. So with this air pollution, we're going to talk about mostly poor air quality, but we're going to be thinking about it with the ultimate lens of trying to improve it, trying to get to something like we can see here, where we go from the smog on the left, where we've got very poor air quality that's going to be very problematic to human health, versus the right side, where we've got kind of that clean air that we're striving for. And part of the reason in some cases that the air quality has improved is because there's been regulation in terms of the pollutants being released into the atmosphere. And the major pollutant that gets focused on the most is going to be probably carbon dioxide, just because it's going to be the most important in terms of global warming. But what we're going to be thinking of in terms of the air quality is mostly going to be looking at different types of pollutants. So we've already talked about carbon dioxide quite a bit throughout the different chapters. We'll see it a little bit more throughout this one as well. But we're going to be thinking of the pollutants for the most part in terms of things that are going to be negatively impacting human health the most, and doing so directly, because of course carbon dioxide is going to be hugely problematic because of the global warming, which is then going to impact human health. But we're going to be more focused on stuff like we can see here, these 6 different pollutants. And then, like I said, with these pollutants, a whole bunch of different types, and they're coming from a whole bunch of different sources. So before we even really dive into this, if we're just thinking about energy, that's going to be one of the major sources of pollution. So we need energy to do pretty much everything, but that's going to, in a lot of cases, since we don't use green energy, that's going to be contributing to poor air quality. Transportation, so planes, of course, going to burn a whole bunch of fuel. Cars as well. Industry, same thing. So we're just thinking about everything that's going to be sort of spewing this stuff out into the atmosphere. And one thing that you may not be as one thing that just may not be at the front of your mind as much is going to be agriculture. You may think of it in terms of pesticides being sprayed and that affecting the air quality, which we'll certainly talk about a little bit, but also just the waste of these different livestock animals. So they're going to produce ammonia, and that's going to be another, along with just these other things that we're going to talk about: ozone, sulfur dioxide or sulfur oxides, nitrogen oxides, VOCs, particulate matter. Just going to be stuff, heavy metals, of course, going to be stuff that's just going to negatively impact human health. And when I lived in Utah, actually, they had extremely poor air quality, especially in the winter, particularly in the northern part of Utah where I lived. And they had one thing that they would describe as cows and cars, because there was a ton of agriculture in that area. So they were producing ammonia. And then there's a whole bunch of cars on the road as well. So just spewing out all of the stuff out of tailpipes that we don't want to be breathing. But then based on sort of the topography of that area, it was essentially just a bowl almost, just surrounded by mountains, nearly 360 degrees. So the air would be very stagnant. And then the ammonia and all of the different chemicals from the car exhausts would just create just terrible air pollution. And with the cars, one reason you don't want to be running a vehicle in the winter, in particular, especially in a garage or somewhere where you're surrounded by snow, where that exhaust can kind of build up, is going to be carbon dioxide production, which is just going to come from the incomplete combustion of fossil fuels. So normally we produce carbon dioxide, but if that process doesn't just go 100%, essentially you're going to get some carbon monoxide mixed in there. And then with carbon monoxide, the reason you need a carbon monoxide detector in your house is because carbon monoxide is going to be colorless, going to be odorless. You're not going to be able to detect it at all yourself. So you need the actual detector to do it. Because if you're exposed to carbon monoxide, it's essentially just going to replace oxygen in your blood. It's going to bind to the hemoglobin, which carries around oxygen. So you're not going to be able to transport oxygen to your muscles and your cells. And you're essentially just going to sort of get sleepy and then ultimately pass out if you don't get out of that area and get some fresh oxygen. And we're saying binds irreversibly to hemoglobin. If you are exposed to carbon monoxide, you do need to go outside, obviously get some fresh air, but over time you will sort of clear out that carbon monoxide and just get back to your regular self. Depending on how much of carbon monoxide you're exposed to and for how long, the effects can obviously vary. But generally, if it's not too much of a exposure, you just go outside for a little bit, you'll start to feel much better. And then another common pollutant is going to be lead. So the biggest source of this was probably gasoline up until the 1980s. So we have unleaded gasoline now because we've removed the lead from it. That's helped remove a lot of the lead from the atmosphere. So we're no longer breathing that in constantly. We're no longer exposed to those levels of lead. And that's going to be extremely beneficial to the health of everybody because there's no safe exposure to lead. So with certain contaminants, there's sort of a little bit of leeway almost where there's not going to be really any noticeable effects up until a certain concentration. But with other chemicals, there's going to be no safe exposure, and lead is going to be one of those. So that's something we don't ever want to expose ourselves to in any quantities. And that's particularly true for children, because if we think about it, children are often going to be smaller. So the same exposure is just going to be worse for them just because they're going to be smaller. So it's going to be a relatively larger exposure. But also because they're still going to be developing. So what they see a lot is when children are exposed to lead, they see decreases in IQ and just brain function overall. So that's, again, one of the main sort of successes of environmental legislation. It is just going to be the removal of lead from gasoline. There are other sources of it. So burning fossil fuels, so burning coal is going to release some of it. Mining is going to release some. Smelting releases some. That's essentially just purifying ore. But the biggest source, again, was going to be that leaded gasoline. And that's also, I have no evidence to back this up, but there are some people that believe one of the reasons that like violent crime and serial killers have kind of decreased over the past couple decades is because they're no longer exposed to quite as much lead. So that sort of helps with some impulse control and just the violent tendencies. That's not a fact, but it is one kind of theory. Another pollutant is just going to be the nitrogen oxides. So we're just going to count these as kind of a large class, and sometimes you may hear them referred to as just NOx, so NOx, NOx. Because with these, we're kind of just thinking of any compound that's going to be nitrogen and oxygen. Doesn't really matter the exact ratio of those. So we could have one nitrogen, one oxygen, one nitrogen, two oxygen, whatever it's going to be. But we'll see a lot of these pollutants, they're going to be coming from vehicle emissions, they're going to be coming from industrial sources, and it's going to be the same thing with nitrogen oxides. What's going to be particularly problematic about these is they do have health effects, but also that they're going to contribute to acid rain. So the nitrogen oxides can be converted to nitric acid, which then just gets essentially deposited down. And then the acidic rain can make rivers acidic, can make soil acidic, which is going to negatively impact plant life. The animals living in that environment as well can destroy certain buildings and structures depending on what they're made of. And we'll also see eutrophication, which we'll talk about more in the next chapter when we're looking at water quality. But nitrogen oxides, you can also, I believe these ones are typically brown. So if you ever see kind of brownish in the air, it's probably the nitrogen oxides. And then the next pollutant is going to be ozone. So this is going to be kind of a weird one, because in certain locations in the atmosphere, ozone is going to be extremely helpful. So higher up in the atmosphere, in the stratosphere, we actually want ozone. We're going to talk about the reason sometimes ozone actually gets depleted and why that's bad. Because up in the upper parts of the atmosphere, so the stratosphere, where that ozone layer actually is, that helps shield us from some of the harmful ultraviolet rays. So the ones that are going to be super high energy, the ones that could cause damage to DNA and ultimately cancer and things like that. So the ozone higher up in the atmosphere, extremely beneficial. But when it's near the ground level where we can kind of breathe it in, there we're going to see health impacts. It's going to hurt us. It's going to hurt plants. So you'll sometimes if you see pictures of plants that have been exposed to ozone, they kind of have spots all over them just because it's damaged the leaves and different parts of that plant. And with this ozone, you can kind of just see some of the reactions that lead up to it. So we've got different chemicals involved, and some of them we've already even talked about. So we've got nitrogen oxides involved, carbon dioxide. We've got a whole string of reactions. And with these pollutants in the atmosphere, they often will be reactive. But we're not going to be focused too much on the specific reactions. The next pollutant isn't going to be exactly a chemical. What we're going to be looking at is particulate matter. And this can actually have a whole bunch of different, have a whole variety of chemical composition to it. Because with particulate matter, excuse me, like I said, we're not thinking about a particular chemical. We're just thinking about very, very small particles. And we're going to sort of classify them based on their actual size. So the two main categories we're going to see is PM 2.5 and PM 10. And those are just distinguishing the different sizes of those particles. So PM 2.5 going to be smaller than PM 10 because those numbers are just referring to the diameter of those particles. So you can see on the right, these are going to be even much, much smaller than the width of a human hair. But with these, they can come from a whole bunch of different sources. They can be dust particles that just come up from the road. They could be dust coming from the, like when I lived in Utah near Salt Lake, there was the Salt Lake Desert. Some of the dirt there would kind of just get swept up. And then with these, we'll also see in some cases very, very small, like water droplets can even serve as kind of particles for different sizes. But the thing with these is just going to be when we breathe them in, they're going to get into your lungs, and then the smaller the particle, the deeper into your lung you can get. And then with these, they've actually measured or they've actually observed particulate matter crossing the blood-brain barrier. So they've actually observed particulate matter in the brain of different individuals. And with this particulate matter, it just has a whole bunch of negative health effects. So it can cause a whole bunch of different problems depending on exactly the size of it, depending exactly how deep into the body it can kind of penetrate, which again, the smaller it is, just the easier it is for it to kind of get deeper and deeper into those lungs and cause more and more of an issue. But yeah, this is just kind of showing that. So we can see with PM10, we're going to consider these coarse. So even though they are very small, we're going to consider these somewhat large. So they'll get into the respiratory system, but they won't really get too deep into it. PM 2.5, going to get a little further. And then when we get to PM 0.1, so extremely, extremely small particles, now they're able to really get into the blood and get transported all throughout the human body. And then sulfur dioxide, this is going to be similar to some of the nitrogen oxides in the sense that it's ultimately going to lead to acid precipitation, which again can cause a whole bunch of devastation to aquatic environments, soil ecosystems, plant life, buildings, statues, whatever it's going to be. And then it's also going to negatively impact just human health. So if it gets into if you're kind of breathing in sulfur dioxide or just kind of exposed to it, it's going to hurt your lungs, it's going to hurt your eyes, going to damage plants as well. And with this, like a lot of them, again, going to be coming from the combustion of fossil fuels. So if we can move to greener energies, we're going to be able to at least reduce a lot of these different pollutants that we're talking about. And then just like the lead, we'll also see this is going to be released during smelting, which again is just purifying different mineral ores. And then the group of compounds that I'm most familiar with, at least from my research, is going to be the volatile organic compounds, so VOCs. And these can be used in a whole bunch of different areas. So fuel, we've got VOCs in oil and gas. Plastics contain VOCs, pesticides. A lot of those are organic compounds that are going to be volatile, that are going to be able to get into the air, chemical manufacturing as well. And with these, we're going to see in some cases they'll actually react with ozone to produce reactive compounds that can cause other issues. But just the exposure to VOCs, we've got kind of some of the ones at the top are going to be more acute symptoms in the sense that there'll be shorter term and more related to the immediate exposure. Where at the bottom, we're thinking more in terms of the long-term health, if this is something that you're exposed to in very high quantities or you're exposed to somewhat frequently. So if you work in an agricultural setting that's constantly spraying different pesticides like these that you're constantly exposed to, you may also experience kidney damage, elevated blood pressure. Depending on the chemical, there's often increases in cancer incidence as well. So there's a whole bunch of negative consequences of poor air quality. And then this is just a picture of Utah where I used to live. So I didn't, this one's just from the internet. It's pretty poor quality, but you can still see what's going on there. We got the mountains in the background. You can kind of see the town a little bit in the foreground, but just the air there, just terrible quality because we've got so many pollutants, and it's not going to be something that people want to breathe. It's going to make people sick. It's going to be an economic burden just because people are going to be having to go to the doctor. People are going to need medical care. They're going to be missing work. So it's just going to cause a whole bunch of issues. And with these, like I said, there's a whole bunch of different sources of these pollutants. There's a whole bunch of other pollutants in addition to just the handful that we talked about. But in 1986, the EPA did establish the Toxic Release Inventory, so the TRI. And this is just essentially a log that basically keeps track of the different releases of these chemicals from, you can see these different sources. But with this, it is self-reported, so there is always some issues with that. And then another common pollutant that we want to talk about is just going to be mercury. So like a lot of the metals, this is going to come from the combustion of fuel, lead as well. A whole bunch of different metals are going to be released into the atmosphere when coal in particular is burned. But there's going to be other sources as well. So even just burning waste can in some cases release mercury. But we're going to see the mercury is going to get into the atmosphere. And then what's actually going to happen is in the ocean, bacteria is going to convert that into methyl mercury. So it's going to convert it into a different form of mercury. And this new form of mercury, this methyl mercury, is going to be able to bioaccumulate. It's going to be able to bioaccumulate just within the trophic levels here. So we'll see much higher concentrations at the top, So stuff like they're listing it here: shark, pike, albacore, halibut. And then even if humans then eat it, we're going to see that process continue even further, one step up the trophic level again. But the reason this is going to be able to bioaccumulate is it's just going to be fat soluble. So once it's sort of ingested by any of these animals, it's going to just sort of stock up in the fat of these different animals. And then as the next one eats it, that process is just going to occur again, just all the way up the food chain. And we'll see this pollutant just magnify within each of these different trophic levels. And then I mentioned the airborne mercury. I like this image because we can also see the draining from the mine. So acid mine drainage often releases mercury. So we can see that process occurring as well. But the thing that's going to make it extremely problematic is just the bacteria converting it into methyl mercury, which now has the ability to bioaccumulate. And then even, we didn't mention it, but volcanoes as well. So the eruption of volcanoes, obviously going to be bad for the air quality just in general, because we're going to be releasing a bunch of particulate matter and a whole bunch of other things, but there's also going to be mercury and some other metals released in that as well. And with the air quality, we're often focused on the indoor environment, or the outdoor environment, excuse me. But the indoor environment is going to be potentially, at least in terms of directly impacting human health, probably going to be even more important, because we spend so much more time inside, at least generally most people do. You can see here the statistics they're putting up. Obviously, these aren't going to be set in stone for every person in every location with the one on the right, but we can see in general, most of our time is going to be spent indoors, and we're actually going to see more pollution indoors than we do outdoors. Some of that pollution may be the same. So sometimes you may have ozone just from it being at the ground level, but we're going to see differences in the types of pollution as well. And with these, the type of pollution or pollutant is going to be dependent on the activity that's occurring within the home. Yeah, so if we just look at some of the main examples, so air conditioners and things like that are going to release different chemicals. And if the room's not well ventilated, those are just going to build up over time. And in some cases, even just pets could contribute to poor air quality. And then the two rooms I would expect to have some of the worst air quality, I would expect the bathroom, because in that room we're using, as it says here, perfumes, hairsprays, cosmetics, air fresheners, things like that. Those are all going to contain VOCs. And then the kitchen as well, for a different reason, because in this case, a lot of the times when you're cooking things, that's going to release things into the air. And in some cases, especially if you're cooking things like meat, that can actually release things that are going to be bad for your health as well. But also to point out, even things just like furniture can release chemicals into the atmosphere. So we've got to consider a whole bunch of different sources when we're looking at the indoor environment. And with this, we also, maybe not so much with the air quality, since it's going to be more or less mixed, but with the indoor environment, one thing that they also look at is the air quality, but also the deposition, I guess, if you want to call it that. So just where different chemicals are going to land, because when you've got different people living in a house or apartment, whatever it's going to be, they're going to be exposed to different pollutants depending on kind of how they live. So in general, the indoor environment is going to impact women, children, and the elderly more often, just because in general, they're going to be more likely to just be inside more often. But then if we're just thinking about chemicals that kind of land on different surfaces, In that case, we'll also see differences just in the way different people kind of operate. So if you have a baby kind of crawling around on the ground, putting a lot of different things in their mouth just as they kind of pick them up, they're going to be exposed to different, to a slightly different environment than an adult would that's kind of just walking around grabbing things like off of shelves, versus an elderly person that may kind of just be hanging out in one room the whole time. So with the air quality, we've got to kind of think about these different sources, but also where people are going to be located more frequently, and things like that. But to jump back to the outdoor environment, with the air quality, one thing that makes it particularly difficult to deal with is the fact that the air moves. So it's not just we release a chemical here, it stays here, we can deal with it here. But once a chemical is in the atmosphere, it's got the ability to move in a whole bunch of different places. And that's what we actually see in the polar areas. So thousands of miles away from anywhere near where some of these chemicals would be, we see them actually bioaccumulating in polar bears and things like that, because this atmospheric transport is possible. So these volatile chemicals, the chemicals that can essentially evaporate into the atmosphere, they then get transported through the atmosphere till they reach an environment that's either going to be high elevation, so it's going to be colder at those higher elevations, where they'll then condense out of the atmosphere and settle down in the snow or the soil, the water, wherever it's going to be. Or instead of elevation, high latitude. So near the poles, where it's again going to be colder, they'll recondense, and then they'll settle down into the water, the soil, wherever it is. And then depending on what the chemical is, it may also have the ability to bioaccumulate within that ecosystem. So with the air pollution, it really is a global problem, because the pollutants themselves, once they're released into the atmosphere, are essentially just going to move wherever they're going to move. Some pollutants will break down. Depends on, could be good or bad, depending on what they break down into. But other ones that are going to be more persistent, those are going to be the ones that are going to be more able to undergo this atmospheric transport. And sometimes it may be referred to as global distillation, because distillation is just essentially using differences in boiling point to purify a substance. So if one thing boils at 50 degrees, the other boils at 100. You can heat it up to like 75 and you'll get the first one to boil off, but not the second one. Kind of what they're showing on the right side here. We're getting these different chemicals. They're going to go into the atmosphere. And then based on their chemical properties, some of them will travel a little, some of them will travel a medium amount, and then some of them are going to travel a lot farther. And in some cases, we'll even see it occur in kind of multiple steps. And that's why it's called grass hopping down here, because we kind of see those chemicals kind of jump in different sort of different steps. And to briefly touch on the greenhouse gases. So again, these are going to be the ones that most directly contribute to global warming, because they're going to absorb the reflected sunlight, keep that energy within the atmosphere, keep that heat in essentially. And we've got a couple different types of greenhouse gases. So carbon dioxide, the biggest one, methane, we've talked about a bit. It's natural gas. Nitrous oxides, we've just talked about. And then we've also got these fluorinated compounds. So hydrofluorocarbons, perfluorocarbons, and sulfur hexafluoride. With these, one of those, specifically the chlorofluorocarbons, these are going to destroy the ozone. So that's going to be another reason why we want to protect the atmospheres, because some of these can actually react with that ozone layer. So up in the stratosphere where we actually want ozone. The chlorofluorocarbons, excuse me, which are used in things like refrigerants, or at least they used to. Now they use hydrofluorocarbons or hydrochlorofluorocarbons, something. I forget exactly what the term is. They all sound very, very familiar. So But with this, like I said, they were used in refrigerants and things like that. They get into the atmosphere, and then they essentially just react with the ozone layer. And with the ozone, you can see this is the South Pole. That's going to be Antarctica down there. Every year there is sort of an opening in that ozone layer that just occurs naturally. But what they saw is the hole in the ozone layer continued to grow and grow, and they were able to determine that it was because of these chlorofluorocarbons. But another example of successful legislation is with the regulation of these. We did see the ozone layer start to come back. So we did see the progress start to get restored there. And then just in general, as we talked about the poor air quality a lot, but this is just kind of highlighting all of those potential different health effects there. And with this, it's specifying in some cases the different chemicals. A lot of the times you'll see that a lot of these are going to go hand in hand. But you can see poor air quality is going to affect pretty much the entire human body in one way or the other. And with this, I should also mention, again, there's going to be a huge economic cost to this because people are going to be sick. They're going to need to go to the doctor. They're going to miss work. And then that's just going to kind of build up. And that's going to be something that the society as a whole ultimately has to deal with and ultimately has to pay for. And that's just what we're showing here. So you can see the pyramid of air pollution effects at the top going to be the most severe. So that's where we're going to see deaths. And there are, I forget what the exact number is, but a much larger number than you may initially expect in terms of deaths. But we're going to see as we go further down this pyramid, as we get towards the foundation of it, we're going to see the amount or the relative proportion of these different effects increase greatly. So at the very bottom, these bottom couple, what we're going to see is those are just going to be sort of in some cases, they may just be affecting the quality of your life. They may not even like prevent you from really doing anything, but it may just make it more difficult for you to breathe in general. May make it so that you can't, if you're like an athlete or a runner or something, you may not be able to run as far. You may not be able to go on hikes, things like that. Or it could be stuff that gets a little bit more severe. So you may actually have asthma attacks. You may need to start taking a certain medicine, doctor visits, hospital admissions. So again, we're seeing just the impacts of air quality just as it gets worse and worse. We're just ultimately going to see worse and worse outcomes until eventually we just get to the worst one, which is just going to be death. And like I said, this is going to have a huge economic impact, because if we just look at, this is for 2018, so fairly recently, the sum of all of these costs, so the deaths from air pollution, the hospital admissions from air pollution, doctor visits from air pollution, and then just the less severe impacts from air pollution, for the United States at least, a couple years ago, all of that added up to 3% of the GDP, so the gross domestic product. Might not seem like a whole lot, but that's going to be an extremely, extremely huge amount to be attributed to just air pollution. So of the entire US economy, when everything was sort of accounted for, we've lost 3% of that just due to the economic costs of that air pollution. And this is just from fossil fuels. So if there's other air pollution that we're not even accounting for in this, that number would even go up even higher. And with this, I don't remember why I put this on this slide instead of earlier, but this is just going to be showing that process we talked about with the nitrogen oxide, or the NOx, or the sulfur dioxide. So we're going to have those be produced from industrial processes, the combustion of fossil fuels and things like that. And then ultimately, we're going to have that mix in with the water, get precipitated down as either nitric acid, HNO3, or sulfuric acid, H2SO4. And in this case, they're just showing that it's killing the trees, but we'll see it's going to negatively impact all of the different vegetation in that area. If it gets into the water, depending on the quality of that water, depending on the location of it, it may not be affected at all really, or it may be affected tremendously, and you may see the pH of that water drop considerably, which could be devastating for anything that lives in the lake or water, river, whatever it may be. But with the acid rain, we should mention, especially for the sulfur portion of it, there has been tremendous improvements in terms of reducing the extent of acid rain, because they've started to use sulfur. One of the main sources of it is going to be coal. They've tried to move towards what's called clean coal or low sulfur coal, just so that we produce less of this sulfur dioxide, we produce less of this acid rain, and we can help protect the environment that way. And then air quality is also going to be impacted by the environment that you're in. So like I talked about when I was in Utah, the location for that was particularly well suited for poor air quality, because we had essentially just a 360-degree enclosure of mountains that kind of just kept the air stagnant, as allowed the pollutants to just build up. And in that case, what it was known as is an inversion, because generally what you're going to see is the earth kind of keeps the air warm. So as we get higher up, we see the temperature decrease. But warm air is going to be less dense, so it's going to continue to rise. And you can kind of see that's what we're showing here. So we're going to see the constant movement of this air. We're going to constantly have essentially a flow from bottom to top, and it'll just kind of redo that process on both sides, kind of just giving us a nice flow. In this case, though, when we've got an inversion, what that is just a warmer air layer above the initial layer. So when we have the air start to rise, since it's colder, it's not actually going to continue to rise. We're going to essentially kind of just have like a cap or a blanket over the top of it. And now what this is going to allow, if there's any pollutants here, it's just going to allow those pollutants to stagnate. And now it's going to be something that we're continuously breathing in. Whereas if we don't have that inversion, now anything that's at the ground level is going to be constantly sort of swept away. So we'll be able to, at least to some extent, protect ourselves from the pollutants. If there's still something in the air there, we're still going to breathe it in, but it's not going to be nearly as bad as when we're looking at something like an inversion, where the pollutants are essentially just stuck there for however long they're going to stay there. And that's why when I was in Utah on the days where there's particularly poor air quality and there was an inversion, it was actually recommended that you don't do anything outside, because just breathing in that air quality, breathing in the particulate matter specifically. One of the professors that I knew would equate it to, like if you went out for a 30-minute run, it would be equal to smoking like a pack of cigarettes or something, just because you would be breathing in so much of that poor air. Like I talked about, controlling air pollution is something that we can be successful at, and is something that we have been successful at in the past, when it's something that we've kind of decided that we wanted to do, when it's something that we decided we needed to do generally. And the biggest thing, or the easiest way to go about it, is just by reducing the production. So if we can prevent pollution from getting in the air, that's going to be the easiest way to handle it, often going to be the cheapest way as well. And what that could be is controlling escapes and leaks. So in different factories, different mining operations, whatever it may be, there's often leaks, often places where these different pollutants are going to kind of go unaccounted for, and they're going to be able to escape into the atmosphere. So if we could go through and actually plug all of those leaks, identify where those escapes are happening, wouldn't be a complete solving of the issue, but would help make a minor improvement in the quality of air. And like I mentioned, one thing that we've done is the low sulfur fuel. So that's helped reduce the amount of sulfur we're producing. reduce the amount of sulfur oxide that's getting into the atmosphere, help limit the acid rain. So that's going to be one example of when legislation and action has been impactful and has been successful in improving the air quality. And one other method that we could use is some sort of carbon tax or just pollutant credit. You may hear a couple different terms for it depending on exactly what we're looking at. And even depending on how they do it, it could look a little bit differently. So in this case, on the left, you can see the old emissions for each factory was 100 tons. Now in this new system where they've got the credits, both of them have to get down to 50. Or there's the option where you can kind of trade. Because again, each of them started at 100. Plant A was able to get down to 25, even though they were allowed to get up to 50. So in that case, they had an extra 25. They would be able to trade that to plant B and then get some money back in that case. So there's some incentive to kind of reduce your pollution, because then somebody else will try to buy it. But then there's even incentive for this company to reduce their pollution so they don't have to pay that extra amount. But again, with this, we're just trying to think of how we can reduce that pollution so it's not even something that we have to deal with in the atmosphere. In addition to this, there are things like carbon capture, where we can kind of put something on the smokestack itself to try to catch any of those pollutants before they even make it into the atmosphere. There's storage underground in some cases where they can kind of try to do something similar where they capture the gas and then just pump it underground so it's no longer in the atmosphere. But with the air pollution, like I said, the amount of deaths that are going to be related to it are probably going to be much, much larger than you'd expect. Over 7 million annually across the globe. And then you can see kind of the breakdown by the different regions. So especially in Southeast Asia. And then this looks like at least part of China. I don't know if that's all China, but part of China, and then India, because those are going to be two locations where they're developing countries, and then they're also using a ton of fossil fuels, so they have particularly poor air quality in those two locations. So that's why we see the highest numbers there. They also have a very large populations there. So in terms of the air quality and then just the number of people being exposed to it, those are going to be two very problematic areas. But you can see even in these different locations in China, there has been a pretty steady decline in the PM 2.5. Because even in those locations, like I said, they're developing, so they're burning a whole bunch of fossil fuels similar to the industrial revolution of the mid 1800s. But they're starting, and in China particularly, they have very high sulfur coal, so that they burn a lot of that. But you can see they've started to make different changes to their energy production, and you can see it's benefiting the air quality at least slightly. It's still much, much higher than you'd want, because the 10 micrograms per meter, still not going to be a great threshold, and they're still well above it, but you can see that they're generally declining.